Hello, my name is Colin Wood, and this is my presentation on predicting energy demand using deep neural networks and time series attention mechanisms. The problem I'm trying to solve is energy imbalance. At any point, the generation or distribution capabilities of a balancing authority might fall under the expected demand and energy. BAs like SRP and APS need to trade energy with other authorities to ensure they can provide low-cost electricity at a moment's notice to their customers. The problem? Predicting what the demand is ahead of time so that trade deals are less risky and customers aren't harmed in the process. In 2014, a group of researchers opened this field to machine learning by using a random forest model to predict the energy prices given a few weather features. In 2016, the artificial neural network was tested on Spain's energy and weather dataset, and 5 years later this was improved by adding an attention mechanism as a hidden layer to solve the Nordic energy demand problem. Despite all of this research, no method for predicting energy demand in the diverse geographical regions of the United States has been made since the 2014 attempt. There are many resources available to perform these predictions. The Energy Information Administration provides standard energy reporting procedures for all balancing authorities in the United States. The NOAA allows us to use their data extraction tool to find a weather station that might help inform our energy predictions. Can we leverage these resources to improve upon the BA's in-house demand prediction? Data was pulled from both the EIA and NOAA for the dates July 1, 2015 till July 1, 2022. For the purposes of this experiment, we will analyze the data collected by APS and measure it against the data collected by the Sky Harbor Weather Station. I remove most of the daily data from the weather set and then backfill on the two I chose to keep. The weather features include things like wind speed, relative humidity, sea level pressure, temperature. Our energy data set measures the generation done by APS and the amount of interchange happening in between APS and all other BAs. In order to merge our data set effectively, the weather data needed to be repaired. There are many instances in which the same hour was reported on 3 times. This is due to varying report types, FM12, 13, 14, SOD, and how some rows are meant to hold hourly data, while others were meant to only report at the end of the day. I developed an algorithm to combine these multiple entries into a singular row, ensuring that the data from each row was collected appropriately and the indexes of our data were set to be on the hour, ready for a proper merge. I then prepared the dataset to be ready for time series supervised learning, introducing another dimension of data by crafting a time lag for each feature column. This provides our model with more context. Notice how the demand at the previous time step, t-1, might help us determine what the demand at the current timestamp t will be. It's time to build our models. First, I split the training data to be January 1st, 2018 through January 1st, 2019. The rest of the data from 2019 till 2022 will be tested. I will then build the following models listed here in order to compare the results with my neural network. I create a pipeline that uses randomized search cross-validation to do a parameter search and a time series split on my regressor. The model is built using 2 LSTM layers, 2 dropouts, and a dense layer, measured with mean absolute error as the metric. The LSTM layers will allow the model to find relationships amongst variables in time. Unlike a traditional RNN, the layer will learn which information to keep and how long to keep it for, whereas the recurrent neural network will simply provide the previous input as an extra dimension of features. I will use RMSE and R2 to score the evaluations on our test set, which will tell us about the amount of error and the variance in proportion between our predicted and actual values. Here we can see the results of our first set of regression evaluations. The random forest ended up performing best in both R2 and RMSE. An R2 score close to 1 and an RMSE score close to 0 is desired. As you can see from the plot, the model is able to properly measure the variance of the energy demand over time with little to no error. Now for the validation of our hypothesis. As you can see, the LSTM energy demand prediction was not better than our random forest. Though it has a reasonable measure of the changes in variance, there is a larger gap between the actual and predicted, showing us why we have a high RMSE score. On the right we see the results of the in-house demand prediction done by APS. Notice the higher RMSE, the lower R2, and the mistakes made in the plot of the first 100 hours of energy demand predictions. Thus we conclude the DNN with LSTM is better than predictions made by this balancing authority APS. However, unexpectedly, using the publicly available US energy and weather data, it seems that a random forest model is still best suited for this problem. Also, it might be beneficial to see if we can train a larger scale model using more time lag dimensions without leading to overfitting. Thank you for listening to my presentation.